Okay, and we are back, so let's get to it. This is part B of class 3. So let's take a look at our first C language program. Now, first off, we're going to get to that program here shortly, but the first thing here is C language was designed to be a systems programming language, and that means it has a close association with being able to do low-level code, but in a high-level language. In other words, it was designed to be powerful. It was designed to be used as a replacement for programming directly in the language of the processor, but it's also designed to be more readable and more maintainable and understandable, but without losing that low-level control. So it can give you almost direct control of the CPU and memory in ways that other languages never could and never will be able to, like Java or Python, or really a lot of other programming languages don't give you that direct kind of one-for-one relationship between what you do in the programming language and what happens in the CPU. C language gives you that. Now, the nature of C language, as we talked about last time, was kind of this ideology of trust the programmer. In other words, the programmer is a systems programmer. If they're using this language, they know what they're doing. And even though it has a reputation of being kind of cryptic and dangerous and promoting bad programming habits, that language or that reputation is not undeserved because it gives you liberty and it trusts you. And in some cases, trusting a programmer is a terrible thing to do, but it was designed for doing systems programming and writing operating systems, where if somebody's going to be doing that, then you kind of have to trust them because they're the ones writing the system that's going to be doing things. So while you can write bad, dangerous, poorly written programs in C, the only reason you can do that is because it's designed to give you power and will let you do that because it trusts you. Now, that means you're going to have to be careful when you write that, and we're going to learn to write good programs in here. We've talked about that a little bit before. All right, so digging into the nature of C language, the first thing is that it uses a lot of symbols for operators, and we're going to learn what all these mean. There's plus and minus. Plus plus, minus minus means something different. Ampersand, asterisk has different meanings depending on where it's used. Greater than is different than greater. Just a single greater than, less than is different. But there's a whole lot of symbols that mean a whole lot of different things, and we're going to learn those. And even though there are those symbols that do things, the language itself has a relatively small number of keywords. In C89, there are only 32 keywords. And if you compare that to a language like Visual Basic, Visual Basic has like 200 and some actually more than 200 keywords. C only has 32, so it's a relatively compact language. And these keywords we're going to look at later on in the class, but there are only 32 of them. Now, the later versions, standardized versions, added a few more, handful more, but the C89 original ANSI standard only had 32. And really, most of the programs we're going to start out with are only going to use some variety of these. And don't worry about what those keywords are or what they mean right now. We'll come back to those later as we learn the language. All right, now the compiling process for C. A program that you write will consist of at least one source file, maybe more when you get to more complicated things. But the way that those get compiled into one project works like this, that you write the source code, and there's two kinds of source files, that, as we'll see in a second here. But here, just think of this as like, here's the main, here's the graphical user interface, here's the non-player character AI or whatever that goes into our game. And then each of those individual C files are going to get compiled, and they get compiled to this .o file, which is an object file. And what the .o file is, it's kind of like the machine code version of that thing up here. In other words, this is instructions ready for the processor to run or execute, except that, for example, if main.c makes a call to something in the non-player character AI.c, it doesn't really know where that is in memory yet because it's in a different object file, so it's not in this one yet. So the last step is these all need to kind of get combined, and where this called some other function that was in another source file, or maybe in the standard library files, it needs to then have that code filled in and all put together into one executable. And that's what this part of the process, this linker program, does, is it loads all of these into memory together. It goes through anywhere there was a a stub that needs to be updated with an actual address. It updates all of those, and now we have an executable that has everything we need all in one file. Now, there are ways to compile this stuff and link it to be a DLL or some other kind of library, like a lib file or a .so file, whatever, shared object file. But the idea here is that we take the source files, they all individually get compiled to object files. Those all run through the linker to give us and get kind of hooked all together into one machine. So this is kind of like building the machine code for each of these separate parts, and then this is kind of connecting them together, which is why it's called a linker. It's connecting together the parts of this that main needs to call, the parts of the GUI that need to call this, the main as it calls the GUI, any of these that use part of the standard library, all that needs to get wired together, and that's what the linker does, which that results in an EXE. And an example of that would be something like, we'll just briefly, let me switch back to here for a second. So this file insight thing where it was making that function call to that, or maybe I should go to web, hold on one second. This function call to the string compare, that string compare wasn't something that was written into the original program, so it had to get linked. And so notice that gets loaded into memory somewhere else, and then the linker just updates the address. So this is the address of it right here. And actually we could jump down to that function code. There it is, jumps to this location. We could jump to that, and we could look at the code that's actually in that place in memory if we wanted to. So the cool thing about the linker is it's going to take care of loading all that into memory, into putting all that together into one executable file for us. And that's useful because we don't have to worry about, we can write our program in as many source files as we want. Those all become part of our project. And when we build that project, it's going to compile all of the ones that need compiled, link them all together for us, and then we'll have this executable that we can use. Okay, so continuing on from there, the compiling process, there are two types of files that are generally used in C programs, C projects. One of them is header files. Those end with a .h extension. So you might have like npc ai.h, and what is usually stored in those header files is not code, like functions that actually do stuff. It usually will have defined data types, other definitions of things, function prototypes, which we'll talk about what that means a little more later on. But those are going to help us use the functionality from other files and libraries usually. In other words, if there's a function that's in, for example, the standard library somewhere that we want to use, we need to pull the function prototype into our program so that our program knows when it gets compiled, knows what that function is supposed to look like. What types of data would we send to it? What types of data does it return? But notice that those header files end with a .h extension. The other type are the actual program code files, and those will have like variable declarations, functions that are defined, all of the code that actually gets executed. And those will often make use of header files, as we'll see here in a little bit. And those file names end with a .c extension. All right. And we'll see a lot more of the mixing and matching those and how to use those to create more complicated projects. Okay, so C functions. So in C, the function is kind of the defining piece of executable code. In other words, every piece of executable code is in a function in some way. And a function is like just like in C, it's kind of like if you would define it in another language like Python, you say def, you give it the function a name, and then you can call it later on. So in other words, C, since everything is functions, it's what's called an imperative or a procedural language, meaning that everything is built up from functions that get called. So all executable code is organized in functions that can be called from other functions. And what is a function? Well, it's just a defined sequence of operations or actions, statements. And functions can include variable declarations, uses of keywords and operators, and calls to others or other defined functions that could be in that same file or in a different file or in the standard library. And so that what it does is it allows us to create layers and build these complex hierarchies of function calls. So for example, you might have your AI non-player character AI might call some math library that does some statistical processing stuff. And that statistics library might call the built-in math library, the standard math library. And all of that might get called by your main.c program that needs to create those things. So you can kind of link together different files that all have different functions and organize it in a way that makes sense. Now, the one thing that is important to point out is that C is not object-oriented, meaning there are no classes, there are no instances of objects. We can do something that's very much like object-oriented programming in C, as we'll see later, but it's not itself an object-oriented language. And that's when we get to the end of the semester, we're going to talk about C++. C++ is like a superset of C that adds, it's really its own separate language. It's an object-oriented superset of C, and that's what C++ is. So we're going to look at that later on, but we're going to focus right now on just straight C, which everything is a function in C. Okay, so that takes us to our first function. Here's an example. This function is a square function. And let's go through the different parts of this. First thing that I want to point out is the use of curly braces here. And also semicolons at the end of the lines. If you're coming to C from a language like Python, you'll be used to using a colon and then indenting things. You'll be used to just ending your lines without semicolons. But essentially, the curly braces are used to group these lines of instructions together, and this is defining it. Let's go through the different parts of this. All right, so the first part, that first int is the return type of the function. And C, unlike a language like Python, is strongly typed, meaning that we have to give that function a type. It has to have a type that we assign to it. And int is just a number. We're saying this is an integer number that this function is going to return. The next part is the function name. So we're naming this function when we define it as square. The next part is the function argument list. In this case, we only have one thing. If we had more, we'd put a comma and list other things. So what we're saying so far is we're going to create a function called square. We're going to pass to it an integer that we're going to refer to in the local scope here. The scope of the function has the variable named num. So we're passing to the square function this integer num, and when this is done, it's going to return an integer as the type that returns. All right, so continuing on, that's the function body, is the code that sits between the curly braces. And then if we dig down a little deeper into that, that's a variable declaration at the top of the function. That's a C language statement that is multiplying num by itself and sticking that into that variable result. And then the last line, there's the return statement, which is actually just returning the value that we calculated back as this integer result that gets returned from the function. And that's essentially how all functions in C are going to look like. They all have to have some sort of a return type. They all have to have this argument list in here or parameter list. And then we have the code inside of the curly braces. And one of the things to notice is that variables in a language like C are much different than in a language like Python. In Python, you can have a variable that in this part of the code, it's holding a number, and then the next line you could change it so it's holding some reference to an object, and the next line you could change it so that it's holding a string. In C, this integer num, it gets created and stored as a block of bytes in memory of that type. And so really, a variable is just a name for a space in memory that's holding data of a certain type. So that variable name refers to a space in memory where data is stored. And that's it, meaning that every variable that you have that's storing data has some address in memory where it lives. And we'll see that a little more later on in the semester. All right, now formatting, white space is ignored. That includes new line characters. So in other words, if I were to go back to this program, I could actually take out all the new lines and run this all together on one big line. Or I could dedent this, and I could put this return up here on the same line as that. I can put it however I want. And the reason for that, white space is ignored, and that includes new line characters. Now, white space can be used as a separator, but it has no other meaning. So, and I have here just like Python isn't, meaning Python uses like the indentation level. It uses the white space as meaningful for things. But in C, it doesn't mean anything. Now, you should still, however, format your code, and that should say and use a readable code style, meaning that you really do not want to have your code be all run together in this unwieldy mess. So kind of looking back at this program here, or this function here, it's not too bad. I might format that a little differently or add some white space or something like that, but the white space doesn't mean anything except to help me look at that code and understand what's going on there. All right, so let's take a quick look at our first complete C program. And here's a C program here, pound include stdio.h. That's a header file that has some pre-done definitions and things like that in it that we're going to make use of. Main is a special function. That's the entry point for execution of an executable. So when you run your program, that's where it starts. It starts with the main function. And then this function, or this program only has one call. We're calling the printf function, which is a standard library function. And we're printing out hello world, \n, and then the semicolon is our end of statement indicator. All right, so this says when this function starts up, the first thing it does is call main, which prints out hello world, and that's the end of main, which is the end of the program, and then it closes. So this is essentially like that program we had earlier that said we changed to say hippo world. This is kind of what that program would look like. Now, what is printf? That's a standard library function. What is pound include stdio.h? That's a preprocessor directive, which we're going to talk about in a second. And remember that all statements end with a semicolon character. So all kind of code that we have will end with that semicolon. Notice that the main does not, the curly braces do not, because those aren't statements. That's a function definition. If this is something we're going to call that does something, we end that with a semicolon. Okay, let's take a little bit deeper look at the preprocessor. And we had a preprocessor directive back over here with this standard pound include standard io.h. And what the preprocessor does is that's a separate first phase of the compiling process that actually edits and modifies the text of the source code before it goes to the compiler. And going back to that for a second, that means that this is saying before you send this program to a compiler, do something to the text of the source code, change it around in some way. And so that thing that's editing and modifying the source code, we're going to talk about why we would do that in a second. But the way to notice the preprocessor directives is they start with a pound sign. Another thing to notice is that semicolons aren't used at the end of preprocessor directives because it's not really, it's like its own little separate pre-compiler that happens before it goes to the compiler. So it's not, that pound include is not a C language statement, it's part of the preprocessor directive statements. Now that can be a really powerful system. It's going to be important for you to understand it. So let me just show you a few preprocessor directives here. So the first one, pound include, we saw that. All it does is opens another file and pastes the contents of that file into this file in that location. So in other words, when I say pound include standard io.h, it says go find the stdio.h file. And if I use these angle brackets like this, the greater than, less than, and greater than sign surrounding it, then that looks in the standard include directory, which has the header files for a large number of the kind of standard C language library headers that are in there. And the reason we had to include that in our program previously, this program back here, is because we want to use this printf function. We don't have to write that ourselves. That's a standard library function we want to use. But if the compiler is going to compile this, it has to know what type of data gets passed to it and what type of data it returns. So to make sure we're using it correctly, it needs that called the function prototype of the printf function needs to be known, or otherwise the compiler can't generate the code correctly for it and make sure we're using it correctly. So that's why we're including that in there. So this pound includes stdio.h line prevents us from having to write that function prototype out up here ourselves every time we want to use it. And in fact, there are a whole bunch of function prototypes in there, some of which, most of which we're not using right now. We're only using one, but notice how easy it is to say, you know, include the header file for standard io.h, and that's going to allow me to use any of the functions that are in the standard io kind of library. That's a standard library with C. Now, if I want to use a header file for one of my own source files, notice I can use double quotes around this instead of the kind of angle braces. And that will, rather than looking in the standard include directory, it'll look in the project directory or the source path that's set up for your system. So it'll look for it somewhere else. And you can actually include a path in here. So if I wanted to, I could say pound include double quote C colon backslash, whatever I want. I could list out some path. That could be an absolute path or it could be a relative path. So for example, I could say pound include project headers / file.h, and it would load that file from that location. So there's two ways to include that. But again, all pound include does is it takes another file and kind of pastes it into the top of this one before sending it onto the compiler. And the main use of that is to allow us to use libraries or code from functions from other, either the standard library or other source files that we created without having to type in all of the function prototypes or define constants or things like that. All right, let's look at one other one. And that one is pound define. And what pound define does, it lets us define a macro or a constant that will be replaced throughout the source code. So in other words, it's kind of like, just like this pound include was like kind of a cut and paste, cut from that file, paste into here. This is doing the same thing, but what this is saying, for example, is, hey, pound define this word nothing as 0. So anywhere in my source code, I see the word nothing, all caps like that, as its own token in the source code. We're going to kind of cut that out and replace it with whatever is over here. So for example, pound define pi as this value. So now rather than having to type this in every time, I can just type in pi, and it's kind of like it does a search and replace for me before it goes to the compiler. And that can be used to make the code more readable, more maintainable. It can also be used for defining things like this, like max players 16. And then if I want to change and recompile my code later on, I could just say, you know what, make max players 32 for this build. I change that one thing and then recompile it. And now everywhere I use this, it's now 32 instead of 16. But note that those are not variables. It's really just replacing the text of, in this case, nothing with 0 or pi with 3.141592653 or max underscore players with 16. It's really just cutting and pasting everywhere it sees these things used. Now, pound define has some more sophisticated uses to make what are called macros, which is still a version of cutting and pasting, but it's a little more capable than that. And we're going to look at that a little bit later. But for right now, just know that that's a preprocessor directive. And all it does is cut and paste things. And again, all of the preprocessor directives just do things to the source code. All right, now, one of the things that I want to show you quickly is if you want to get started with C language and start playing with it, there's two things I would suggest. One is this online GDB compiler that lets you experiment with really simple programs and do things all from your web browser without having to install anything. And one of the things, other things though, since we're going to start doing some more complex projects later this semester, the other thing I would suggest is downloading a C language IDE. The one I'm going to build this on or do a lot of our examples on is this thing called Code Blocks. And the reason we're using that is it's free, it's open source, it's cross-platform. So if you're on Mac or Linux or a PC, you can use that on any of those equally as easily. And to download that, basically just go to codeblocks.org. You can go to the download section and download kind of some version 2.6 of that. You could get an older version too, it wouldn't really matter. But one of the things that you're going to see a lot of possible options there to download. If you don't have a GCC compiler already on your machine, get the one that's labeled like this, Codeblocks 2.03 min. It'll be the one that says min.gw, and it'll have setup.exe. So if you download that, run through the setup, that'll include the IDE, meaning the code editor, and the compiler, all as one download without you having to get them separately. Now, if you don't want to mess with that for right now and you just want to experiment with stuff, you can use this online GDB thing here. And let's just take a quick look at that. So let me switch over through that quickly. Okay, so notice that when you go to that online GDB, it'll actually bring up this Hello World program all on its own. And if you want to try that and see what it does, you can click Run. And then down here in this window, you'll get the output of it. So notice that I can actually make changes to this. For example, Hello World, exclamation mark. I could put like a \n here if I wanted to. And now if I want to run that, I run it again. And now I get a different result from that. So you can type in whatever code you want in here, get it to do whatever you want, and test things, try things out. So for example, we could put our square function in here, int square, int num, and then inside the parentheses here, say int result equal num times num, return result. So there's my function down there. Now I'm going to call that function up here. So I'm going to add another printf. I'm going to say, let's do 15 squared is %d, which is a format specifier for decimal integer. And then here I'm going to call square, the square function, and I'm going to go and put 15 in there. And then we need our semicolon at the end of our line. And now it will say hello world, and then we should probably put another new line at the end of this so they're not run together. So notice that printf does not add new lines automatically. It's up to us. So this is going to say hello, and then on the next line world, and then on the next line 15 squared is, and then we should see what the result of that is because we're getting this to calculate. Now, there is one thing that I want to point out now, and we're going to look at this a little more later on, is that this function, since we're using it up here, we need to have it declared before we use it, which if you're used to Python, you're used to the functions are usually declared at the top and they're used below. But in C, it allows us to have just the function prototype. In other words, the compiler needs to know what is the return type of this and what are the parameter count and types of this to make sure it's used correctly. So in order to do that, we're going to add what's called the function prototype for this up here, which is really just the kind of definition line of it with a semicolon. So this is saying, hey, there's going to be a square function that returns an int and accepts a parameter that's just one int. And then, because otherwise the compiler is going to guess about how this thing is used, and it could guess wrong. And it's also going to give us a warning when we run it. All right, so let's run that and see what it does. And there it is, hello, next line world, 15 squared is 225. And so you can test things out in this and use it. The only annoying thing about this is you'll have to see these ads, like this Simply Safe thing will show up, or there might be an ad for Microsoft Azure or whatever that shows up. And you can actually create an account on here and then save your programs on here and reload them if you want. And you can also debug the things on here. So to debug stuff on here, it'll basically let you go through. You can see the variable values kind of over on the side. And notice down here you can do step over, step into. You can do start here. So I'll click start, and that ran at full speed. But if I wanted to, I could actually run the thing in the debugger. I could kind of go kind of one step at a time. You can see what's in the variables. And so this can be a useful program for doing stuff like that as well. All right, now, and we're going to play around with that and use that a little more later in the class as well. The other thing, remember, I would suggest going ahead and installing code blocks if you can, because we're going to use that later on in the semester. All right, so let's finish up there. That's all we're going to do today. Make sure to look out for any quizzes that are on the thing. Next class, we're going to dig a little bit further into C language, and you're going to have some lab time to work on your first lab assignment. So that's it. So stay safe, and I'll see you next time.